Lecture 9.2, Taylor Series. Brooke Taylor was an accomplished musician and painter. He did research in a variety of areas, but is most famous for his development of ideas regarding infinite series. Suppose we wanted to find a fourth-degree polynomial of the form p of x equals a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus a sub 4x to the fourth that approximates the behavior of f of x equals ln x plus 1 at x equals 0. If we make p of 0 equals f of 0, and the first, second, third, and fourth derivative is the same, then we would have a pretty good approximation. So if f of x equals ln x plus 1, f of 0 equals ln 1, which is 0. If we take the form p of x equals our series, p of 0 would be a sub 0, because all the terms except the first one would cancel out. Therefore, a sub 0 must be 0. F prime of x is 1 over 1 plus x. F prime of 0 then is 1 over 1 or 1. P prime of x is the derivative of our original series, or a sub 1 plus 2 a sub 2x plus 3 a sub 3x squared plus 4 a sub 4x cubed, as we took the derivative term by term. P prime of 0 must be a sub 1, because the last three terms cancel out. Therefore, a sub 1 must be 1. The second derivative at x is negative 1 over 1 plus x quantity squared. If we put in 0 for x, f double prime of 0 equals negative 1 over 1 or negative 1. Once again, we take the derivative of our previous series to get the second derivative. And if x equals 0, all the terms cancel out except the first one. So we get p double prime at 0 equals 2a sub 2. Therefore, a sub 2 must be negative 1/2. F triple prime of x is 2 times 1 over 1 plus x quantity cubed. So f triple prime at 0 is 2. Taking the derivative of the previous series, we get p triple prime of x is 6a sub 3 plus 24a sub 4 times x. So the third derivative at 0 is 6a sub 3. Since the third derivative should be equal to 2, we solve for a sub 3 and get a sub 3 equals 2/6. And I realize that can be reduced, but for the moment we're going to leave it 2/6. The fourth derivative at x becomes negative 6 times 1 over 1 plus x quantity to the fourth. So the fourth derivative at 0 is negative 6. Taking the derivative of the third derivative, we find the fourth derivative of x is 24a sub 4. So the fourth derivative at 0 is still 24a sub 4. Since the fourth derivative should be equal to -6, we solve for a sub 4 and get -6 over 24. So inserting our values for a, we find our approximation p of x equals 0 plus 1 times x minus 1/2 times x squared plus 2/6 times x cubed minus 6 over 24 times x to the fourth. Simplifying, we get p of x equals 0 plus x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4. And we notice a clear pattern there, so if we wanted to, we could extend this to more terms. Now comparing this to our original function, which is f of x equals ln x plus 1, if we plot both functions, we see that near 0 the functions match very well. So here we have the graph of f of x in blue and p of x in red. Now, of course, when we get very far away from 0, even just 2 or 3 units away, the approximation is not good at all. But near 0, the curves match pretty well. In fact, if we zoom in, we see that between -0.5 and +0.5, the curves line up almost exactly to the naked eye. Our polynomial 0 plus 1x minus 1/2 x squared plus 2/6 x cubed minus 6 over 24 x to the fourth has the form f of 0 plus f prime of 0 x plus f double prime of 0 over 2 x squared plus f triple prime of 0 over 6 x cubed plus the fourth derivative of f at 0 over 24 times x to the fourth. Or we could write it this way: f of 0 over 0 factorial plus f prime of 0 over 1 factorial times x to the 1 plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed plus the fourth derivative of f at 0 over 4 factorial times x to the fourth. Note that 0 factorial is 1, which helps us keep our pattern consistent. And we could write an x to the 0 on the first term, but x to the 0 is 1. This pattern occurs no matter what the original function was. The Maclaurin series, generated by f at x equals 0, is this series. P of x equals f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial x squared, and so forth, or the summation from n equals 0 to infinity of the nth derivative at 0 over n factorial times x to the n. If we want to center the series and its graph at some point other than 0, we get the Taylor series. The Taylor series is generated by f at x equals a. So what we've done then is shift the graph a distance of a to the right. Note that the Maclaurin series is frequently referred to as the Taylor series centered at 0, because the Maclaurin series is just a special case of the Taylor series. Colin Maclaurin, who lived from 1698 to 1746, was born in Scotland and started college at age 11. He finished his master's degree by age 14 and became professor of mathematics at the University of Aberdeen when he was 19. He was later a professor at the University of Edinburgh. Maclaurin held the record as the world's youngest professor until 2008. Maclaurin was a contemporary and friend of Isaac Newton and made extensive use of infinite series in his studies of mathematics. The Taylor series expanded around zero is sometimes known as the Maclaurin series. Example, y equals cosine x. F of x equals cosine x, so f of 0 equals 1. Taking the derivative, f prime of x equals negative sine x, so f prime of 0 equals 0. The second derivative is negative cosine x. The second derivative at 0 is negative 1. The third derivative is sine x, so the third derivative at 0 is 0. The fourth derivative is cosine x, and the fourth derivative at 0 is 1. Now, using our standard Maclaurin series, which we just learned, we get p of x equals 1 plus 0x minus 1x squared over 2 factorial plus 0x cubed over 3 factorial plus 1x to the fourth over 4 factorial. Continuing the pattern, we get plus 0x to the fifth over 5 factorial minus 1x to the sixth over 6 factorial. Eliminating the terms with coefficients of 0, we get p of x equals 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. And continuing the pattern, we get plus x to the 8 over 8 factorial minus x to the 10 over 10 factorial. And if we wanted to, we could keep adding terms for as many terms as we wanted or needed for our desired degree of accuracy. Now let's graph our approximation to see how close it comes to our original function. First, we graph y equals cosine x. Now we'll graph our approximation. But first, I'll just graph the first term, p of x equals 1. We see that this is a good approximation if we're very close to x equals 0. But away from the origin, it's not even close. If we plot the first two terms, we see that already our approximation is beginning to match the original function near where x equals 0. If we graph the first three terms, our approximation is a little better. 4 terms is better still. With 5 terms, our approximation matches a little further out. And with 6 terms, it gets even better. So here we see with 6 terms of our power series approximation, the approximation, which is the blue curve, matches the original function, which is the red curve, very closely from x equals negative 3 to x equals 3. The more terms we add, the better our approximation. Hint: on the TI-nspire, the factorial symbol is menu 5 probability, enter. Or in the menu accessed with this key. It's the question mark exclamation point key, for lack of a better name. Example, y equals cosine 2x. Rather than start from scratch, we can use the function that we already know. Substituting 2x in for x in our approximation for cosine x, we get p of x equals 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial plus 2x to the 8th over 8 factorial minus 2x to the 10th over 10 factorial. Example, y equals cosine x at x equals pi over 2. Because our approximation will be centered at pi over 2 instead of 0, we cannot simply substitute into our original series. So we start from scratch. F of x equals cosine x. F of pi over 2 equals 0. F prime of x equals negative sine x. F prime of pi over 2 equals negative 1. The second derivative is negative cosine x. The second derivative at pi over 2 equals 0. The third derivative is sine x. The third derivative at pi over 2 is the sine of pi over 2, or 1. The fourth derivative is cosine x. And the cosine of pi over 2 is 0, so the fourth derivative at pi over 2 is 0. Our series becomes p of x equals 0 minus 1 times x minus pi over 2 plus 0 over 2 factorial times x minus pi over 2 squared plus 1 over 3 factorial times x minus pi over 2 cubed. Remember, because this series is not centered at 0, but is a Taylor series centered at pi over 2, we don't simply use x in the series, we have to use x minus pi over 2. So simplifying, we get p of x equals negative x minus pi over 2 plus x minus pi over 2 cubed over 3 factorial minus x minus pi over 2 to the 5th over 5 factorial. There are some Maclaurin series that occur often enough that they should be memorized. They are on your formula sheet. When referring to Taylor polynomials, we can talk about number of terms, order, or degree. Here our example is cosine x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. This is a polynomial in 3 terms. It is a 4th order Taylor polynomial because it was found using the 4th derivative. It is also a 4th degree polynomial because x is raised to the 4th power. The 3rd order polynomial for cosine x is 1 minus x squared over 2 factorial, but it is degree 2. The x cubed term drops out when using the 3rd derivative. This is also the 2nd order polynomial. A recent AP exam required the student to know the difference between order and degree. The test didn't ask the question directly, but it did ask for a polynomial of a specific degree. Students who misinterpreted the question attempted to find a polynomial with that specific order rather than degree, resulting in additional work, time wasted, and an incorrect answer. The TI-nspire finds Taylor polynomials. The command is Taylor expression, variable, order, and as an option, the value or center of the polynomial. You can find the Taylor command by using Calc09, or the Taylor command can also be found in the calculus menu, but the catalog uses fewer keystrokes. For example, we find the Taylor polynomial of cosine x with independent variable x and the sixth derivative, or the sixth order. The calculator returns 1 minus x squared over 2 plus x to the fourth over 24 minus x to the sixth over 720. To find the Taylor polynomial for cosine 2x with independent variable x and order 6, we get 1 minus 2x squared plus 2x to the fourth over 3 minus 4x to the sixth over 45. And finally, if we want to use a center other than 0, we can try the Taylor polynomial of cosine x with independent variable x, fifth order, centered at pi over 2. And the calculator returns negative x minus pi over 2 plus x minus pi over 2 cubed over 6 minus x minus pi over 2 to the fifth over 120.